In Chapter 3, we're going to learn how to reverse complement a string of DNA. And so this is going to have a lot to do with manipulating strings, as you would imagine. Let's take a look at the REVC challenge here on the Rosalind site. And it's pretty straightforward. It says A and T are complements of each other, as are C and G. And the reverse complement is formed by reversing the symbols and then taking the complement of each symbol. So given a string like this, they want this as the output. So I've tried to show here, given that string that they gave us, showing you side by side the complement for each base. So A goes to T and C goes to G, and vice versa, T goes to A. The DNA is usually read from the 5' end to the 3' end, and so the complement would be from the 3' to the 5' and taking the complements. And so this is what we're going to be trying to do, and along the way we're going to talk about how to implement a decision tree. Earlier we did that using if-else statements. We can write that same idea using a dictionary for a lookup table and shorten up such that kind of logic. Then we're going to talk about how to dynamically generate lists or strings, how to use the reversed function, how strings and lists are very similar to each other inside Python, and how to generate a list using a list comprehension. Then there are a couple functions in the string class, one called makeTrans, and then we can use that to translate a string. And finally, we're going to introduce the Bio.Seq module from Biopython, and that is going to basically take care of all the work for us, but it's important to know what it's doing, and there's a lot of things that we'll learn along the way. So we are going to do this manually first, and then we will be able to appreciate how easy it is to use someone else's code. So to get started, go into the O3 directory of the GitHub repository, and the first thing that you'll need to do actually is to source.venv. In the parent directory, source.venv bin activate to activate our virtual environment. I'll do the same thing over here, source venv bin activate, and then go back into same directory. And I'm showing here to copy the first solution to the program called REVC. And that is important because for our testing. So let's run the REVC with the -- help and look at what the arguments it takes. It looks pretty much exactly like the very first program that takes a string of DNA and printed the number of bases in the string. This time we're going to take a DNA, and you see here that it says an input sequence or a file, so it's the same kind of trick that we were using before. And if we run this right now with the string input from Rosalind, we should see the reverse complement here printed out. And as the help indicates, this will also take an input file. And so if we cat this file, this first input file, we see that is the string from that we just used in the first example. So if we were to use this on that input, then we get the same output. So that is how our program should work. There is one little extra wrinkle. I want you to be able to handle upper and lower case. So if we print it out like that, I want to see the lowercase versions of those preserved. To get started, I'm going to use new py, and I'm going to tell it to force to overwrite this program, and I'm using this as the purpose of the program, and so I'm going to run that. And now I have a default version of the program that has a bunch of stuff we don't need, and at this point I would challenge you to use the tests that are provided to try to create the program as it should work. And so if you want to run PyTest at this point, you will see that it pass a couple of tests, but there are several more that you need to handle. And without running it with any flags, it ran all the tests, and you see here that it did pass a couple. Oh no, it's saying actually it's failing 100%. So there's quite a bit of work here for you to do. If you want to run this on your own, if you want to write it on your own, I definitely encourage you to give it a try. That is the point of all of this. And if you want to see what's going on in the tests, let's just take a look for a moment here. Let's take a look at the def test under uppercase, and what we will see here under tests are the REVC. Looking at the test uppercase, it is running the program. So we've seen this before. If we jump up here to run, the program is called revc.py, and it's determining here if it needs to put Python in front of that if we're on Windows platform. Else we're just going to run the program with the /. And there are a couple of tests here. There's an input file that has the test that's going to be going into the program, and then there's an output file. And I often do this when I'm writing tests because sometimes those input and output strings can be quite large, and so putting them as raw text into my test files can be really cumbersome. So if you're writing a program that say parses some big FASTA file, well, you don't want to put a whole huge FASTA file in your testing, but you might want to put 100 sequences in there, and would be really burdensome to hard code that as a string inside your Python code. So it's nice to just put it as a test file here that you can read at runtime. So let's jump back to the uppercase. What we'll see here is that when we run this with this uppercase text, we expect that the return value of running the program should be 0, and that this should be the string it prints out. And then we get into some of these tests here where it's looking at the input file and then the expected file, and it's running this with the file as the argument, and then it's asserting that the output from that is equal to opening the expected file, reading it, and stripping off the trailing new line. So that is how the tests run, and if you feel like you know what to do, I definitely encourage you to go ahead and run off and give it a shot. If you want some more help, just stick around, and I'll work on that with you. So first, let's talk about how do you iterate over a reversed string. We've already iterated over a string in the DNA program. We were able to use a for loop for that in one instance, and so we know that it's possible, but we want to be able to go over the string in reverse. So let's talk about that using the REPL, and I'm going to type P3. It's an alias that I have for Python 3, and I'm going to assign the input string that we've been using here to a variable called DNA. And if I say DNA, I can use this subscripting with square brackets, and I can start from 0 to 2, and it's going to give me the first 2 characters. Now, something to keep in mind is that we are working with a 0-based offset language, so 0 is the first character and 2 is actually the third character, 0, 1, 2, but the end position is not included. So 0, 2 kind of looks like it takes the first 2 characters, and it does, but it's technically, if you really think about it, that's 3 positions, but the ending one is left off, and it's 1 less than the ending, and that's kind of definitely confusing, and I was going to say for beginners, but it's honestly confusing for me as well. So it's just something that you have to remember when you're working with a language like Python, which is like most general programming languages. So if I leave out the start position, it just starts from the beginning of the string. And if I leave out the stop position, like say I want to go from the 4th character to the end of the string, I don't have to put the end of the string, the length of the string. I can just leave it out entirely. And so I can actually do some interesting things, like I can index negatively. So if I want the last two characters, I can say start from -2, and you see it's giving me GT, and I don't have to give it the end of the string, so I just leave that off. So what happens if I leave out both of those? Well, I actually get the whole string. And what's interesting here is I get a copy of the string. That can be important sometimes. This is one way to copy a string if you want to make sure that you're not taking a reference to a string. And that can be useful. So you can also have a third argument here. If I want, I can tell it the step size. For instance, I could take every second character if I wanted with a step size of 2. One of the interesting things here is if I use a step size of -1, I actually get the reverse of the string. So that's some really, to me, kind of a very strange way of indexing and iterating over a string, but that is the syntax that Python decided on. And so that is one way that we've been given to go over to step through an iterable, a string like that. So there is also this function built into Python called reversed, and as you can already see here in the text, if I say reversed of DNA, what I get back is a reversed object at this hex number. And you were probably expecting that you would actually see the string being reversed. And I talk a little bit here about that this is a lazy function. And this is an iterable, it's an iterator that will create the iterable when we actually need it. And I have a link here to Python's functional programming how-to. And this is really, I mentioned just slightly that I don't like object-oriented programming, and perhaps I said that I prefer more of a functional programming style. And what does that mean? Well, it means I pretty much just use functions as much as possible. And this has a whole write-up on the parts of Python that make it really useful for writing style in the style of functional programming languages. And so one of the things that you will encounter in functional programming are things called iterators, and most often they are lazy. So it's really just a promise to create the string when you need it. And if you think about it for a second, if you read in the entire 3 GB genome, human genome, and you want to reverse it, what do you have to do? Well, that entire string needs to be living in memory, and you need to be able to jump to the very end of it and then go backwards over it. So it's actually could be an expensive operation to reverse a string. So if you say you want to reverse something, Python's just going to wait until you actually need to do it. So how can we tell it we really want to see the reversed DNA? Well, we need to get the data out of there. And a reversed object is an iterator, so one of the things that we could do is feed it to a join operation. So let's just look at the output of this. Let's say we have some sort of I'm going to just call it X here, and it's going to be a list of I can actually do this. I'm just going to say A, B, C, D. And I force, by forcing A, B, C, D into a list context, I've actually turned it into an actual list of characters. And so if I wanted to, I could, for instance, join X on double colons, and it will put double colons in between it. So what I've done here is I've said, take the reversed of DNA and join it on the empty string. So I'm basically taking this list of reversed characters, and I'm putting them back together on the empty string to create a new string. And if we look at what is the type of that, it has created a new string for us. So that is one way to turn the reversed object into a string. Another is to use what we just saw there on list. So if I say list of this, then it's forcing reverse to give me the results of it in a list context. And so that is one way to get that entire list back. Now, one of the things that's kind of funny is that the thing that went into it was a string, and the thing that's coming out of it is a list. And there's just something you have to get comfortable with Python, that it's really kind of interchangeable between lists and strings, and to an extent a string is a list of characters, and so it's actually pretty useful. In some ways it can bite you because maybe you are using one type as the other in a context where you shouldn't be, but for the most part, if you're careful, this is actually pretty useful. So and I show here that we can actually just take any string, like our DNA string, and turn it into a list, and it explodes it into an actual proper list. But it has created a new list from the string. So if you have a huge string, like your entire human genome living in memory, and then you put that into a list, a different list variable, now you've more than doubled the memory footprint of your program. So it's something that you need to be concerned about. So how can we use this to our advantage? Well, we could start by creating a variable that will hold the reverse of our string, and we could say for base in reversed DNA, we can add that to plus equal to base. We can add base to rev, and then if we look at rev, we see that we now have the string in reverse. So it starts off with this T and ends with AAA, and that's the AAA there, and there's the T at the beginning, at the end. So that is one way to build up, that's another way to build up a string from the reversed DNA. So it doesn't, like I said, it doesn't matter if we reverse the string first and then complement, or vice versa. So we now have a few different ways that we could reverse a string and create a new string, and now we need to figure out how to complement. And so because I've insisted on handling both upper and lowercase, this decision tree looks a little ugly, but this works. So one way you could go about complementing each one of the bases is that you go through the reverse DNA and you say if the base is equal to A, then instead of adding A, we're going to add the complement of that. And this code works, and it is actually in the solution one. Let me just grab it real quick. And I'm not sure if I can paste this in. Yeah, it's not very happy about that. So let me do a little trick real quick. I'm going to outdent this so that I can grab it and paste it into the REPL, and now it will be happy. Oh, and it's not happy about args, so we're just calling this DNA. So let me try one more time. And REVC is not defined. Let's try one more time. Okay, REVC is now equal to the reverse complement. Let me just undo those. I don't want to show too much of that solution because I'm hoping that maybe you'll run ahead and write it on your own. But if you are still following along with me here and you want some ideas about how to, one way that you could take the complement, this is one, and I'm giving it to you. And so what we've got here is we're still working with DNA, and we're reversing over DNA, and we're just pasting in the complement, handling both upper and lowercase, and keeping them upper and lowercase if that's what we want. And so if we were to start off with a different DNA string like TTTTGGT, just put in some, and I'll just throw in a couple more characters, and let's just put in that last, oops, you know what, I need to overwrite REVC again and then try it again, and then let's look at what REVC comes out to be. It has been reverse complemented. Very cool. And this was the DNA that we gave it. So this does work. And if I were to put that, if I were to fix up the get args to accept a DNA string from the command line or from a file, and then use this code to print out the reverse complement, it would pass all of the tests. And we looked at the test uppercase. Here's what the test lowercase looks like. So that is something that you should keep in mind as you're writing your program. And then I pointed out here how I'm using the file to read the input and expected output of the program. And so if you want to go ahead, you should write this yourself. Otherwise, let's just talk for a moment about refactoring. There's a lot that we could do to make this program much, much better. For instance, we could replace this entire if-else chain with a dictionary. And we can rewrite the for loop as a list comprehension. These are, if you have already figured out how to write the basic one, or you've using the code that I've just shown you, go read about how you could use dictionaries as lookup tables. Go read about what a list comprehension is. Look at the string translate method and try to figure out how you could use that to change the string. And you might be tempted to use string replace, which is something I talk about in this section. And so figure out why string replace doesn't work, but translate does. And then finally, go read about Biopython and look at the seek object and see what you can do there. And the reason why I'm telling you to do this on your own is because, quite frankly, you'll learn more if you teach yourself. All I'm able to do as a teacher is to bring you to where the knowledge is, but I can't learn these things for you. So if you really want to challenge yourself, you go read the documentation. And in this age of AI agents writing programs, you could certainly have an agent write these programs for you very, very quickly. But you won't learn anything, and you won't be able to apply the ideas to future problems that you're trying to solve. So I encourage you to teach yourself by reading documentation. All right, hopefully you've paused the video and have written a bunch of solutions and tested them, and you are ready to compare notes with me. So here is how I'm going to change up my program. I've got my REVC, which is the default that came out of the new PY. I'm going to change my arguments to simply have a string that I'm going to call DNA. And that is going to come from a positional argument that I'm going to call DNA here. The metavar is going to be uppercase DNA. And I'm going to say that this is an input DNA sequence or file, so that my user knows that they can give me a file. And I'm going to parse those into the args. I'm going to say if os.path.is file, and I need to remember to import os real quick. Oh, and I don't need text.io since I'm not using a file argument. I'm going to say if args.dna is a file, then args.dna is equal to open args.dna, read it, and then strip off rstrip the final new line. And then finally I will say that the DNA position is equal to args.dna. And with that, I have a getArgs function that will do a lot of nice things for me. Let's just talk about a couple of the things that it will do. If I try to run my REVC now with, for instance, this string, and let me just go down here and get it to where it will print something useful. Let's just print args.dna to start off. Always a good place to start. So we'll give it, let's see, I like to use the same string if I can. Go find that. There's my DNA string. So let's use the same string. Whoops. And right now it just prints out the same string. if I were to, for instance, run this, let me run this with that string, and I'll put it in there twice. One of the things that we get from this is that it does not allow me to use more than one argument. So I'm forcing my user to give me exactly the input that I expect. Now, obviously, they could do something like they could say, what is the reverse complement of a number? And we're not doing anything to validate that this is actually a string of DNA right now. It looks like a number to you, but it's actually a string of characters. It's not been turned into a numeric value yet. So that's really just a string that we're giving it. The other thing, though, that we have is we have tests inputs, input 1. And so if I run it with that, it's going to see that that is an input file, and it's going to read it for me. So pretty decent program that we have so far. And if we run pytest xv, we see that we're passing. The fact that we created the right program name, it has a usage, and it dies with no arguments. And then we're failing on the uppercase test, and we looked at that, so we know what it's expecting, and we understand why it's failing. So we looked at solution 1, and that was one way. Let me go into solution 1 real quick. And so here I'm using VI, and I'm able to open up a second window, a second editor here. And so that is what's going on here. I'm just jumping over here so that I can grab this part of the code, go back to my program, and instead of printing this, let's center it on this. I'm getting the arguments. I'm initializing a REVC variable, just like I did in the REPL, and I've pasted in that decision tree using if and else if, and then I print the rev complement at the end. And now if I run this, did I save it? No, I did not. I need to save my program, and now I'm passing all of the tests. And the tests include uppercase, lowercase, as well as using the input files as arguments. So that's a pretty decent solution. There's not a lot to talk about here. So I'm just going to go to the next solution, which is more interesting. And that is replacing all of this with a dictionary lookup. So let's close this, jump back into Python. I'm going to have to carefully copy this because of the new lines here. So let me start off with, I'm going to start off with creating a trans table. I'm just going to have to type that, aren't I? And then it's a dictionary. And the way to write a dictionary is to have the keys follow in as a string, or however, whatever type you're using. Here we're using a string followed by a colon, followed by this will be the key, and this will be the value. Now normally it's very common in source code to have each key value pair on a new line, but just for the purposes of putting this into the text of the book and saving time, I put several key value pairs on the same line. And one of the things that allows me to do is that I'm showing you here A goes to T, C goes to G, G goes to C, and T goes to A. And then on the next line, I'm showing you the exact same thing, but with lowercase. And so if I say, what does trans look like? It's printing it all on one line for me. By the way, if there's a handy module I use a lot called pprint. So it's for pretty print. So if I from pprint import pprint, and I pprint trans, then, in this case, a lot of times it will print it with more new lines, and it's a little easier to see. It didn't do that in this case. So what I could do now is, instead of doing if-else if, I can say trans at A, so translating A to T, that works. But we have this problem. What if I were iterating over a DNA string and I were to come across an IUPAC code like R? Then I'm going to get a key error if I try to access my dictionary using keys. So if you'll recall, there's a safer way to do this, and that is using a function called get. And if you will remember, it doesn't seem like it returns anything when you say get for a key that doesn't exist. If we ask what the type of that, it's actually returning the none type. And so what we could say is get R or just give me R. So in the case where there is a base that we don't know, we'll just not translate it. That is again, that is a decision. You might want to have your program blow up. Maybe you want to just let it raise a key error, especially if you're just writing something quickly, kind of a one-off script. Maybe you want it to just fail so that you know that there's some data that you're dealing with that you weren't expecting. And it would be a real problem to translate IU-PAC codes, or you've suddenly been given protein sequence instead of DNA sequence, or RNA sequence instead of DNA, and you need to know that there are bases in there that you're not expecting. So this is a way to not trigger an exception, but there may be cases where you want to just allow your code to trigger an exception and let it fail. Again, calling that the happy path. We're just trying to write a program that only handles good data and doesn't bend over backward to handle every possible failure case. There's a good case to be made for letting your code fail. So if we look at this code, so for base in this string, and remembering that we don't have to do anything special to iterate over each one of the characters here, what we're going to do is print the base, and I want to see basically this table here, where I want to see the base A, and I want to see what it translates to. And if I go back and put in that, for instance, that R here, and run that again, then we see here it just prints the R. So this is another way, a much shorter way of writing that whole big else if. We've replaced all of those lines of code with just really one line of code, and we have handled even the else. If we go back and look at that else, we were just using the base as given. So we've handled even that. Pretty handy. And if we ever were to want to expand this tree, all we'd have to do is add one more key value pair to our trans dictionary. So that is one way to print this table. So I want to create the complement of this. So like I said earlier, it doesn't matter if we complement first or reverse it first. So for base in my string, instead of printing the base, I want to add this to complement. And if I say what is complement, it has been complemented. So I could now reverse it. So if I say if I force into a list context what is the complement, and then I can join that back together here, like we saw earlier, to get the reverse complemented string. And what I will say about writing code like this is that it's very, very clear reversed complement. It's right there. So it's very clear what this code is doing, even if someone wasn't quite sure what was going on here. Why do I need to join this thing called reversed? Wouldn't I just get a reverse string? Well, you don't even have to know all that. You just see that you are getting reverse complement. Very useful. So if we put all of this into our program, let's go back into our program now. REVC. And this time I open up solution 2. Now it looks like this. I'm going to grab these lines of code and I'm going to go put them into my program. I can get rid of the original parts. So there's my translation table, and I'm showing a couple different ways of writing this. So what I was just showing you was complement is a string. So I'm going to show you two different ways to do this. One, complement starts off as a string, and I'm using the plus equal to add transget base with a default of base to complement, and then I'm going to print the joining of the reverse complement. And if I run this, it will pass all my tests. This is the point of having these tests, and so that you can keep playing around with your program and seeing, does it still do the thing it's supposed to do? So what I point out here in this chapter here is that there's we've already talked about that strings and lists are kind of interchangeable. And so if instead of starting this off as a string, I were to create it as a list, I can actually, okay, watch this. I can actually continue to do the exact same thing here. I can use plus equal to add to a list. So let's just look at that real quick. If I have x is equal to an empty list, and I say x is plus equal to e, x now has e. And if I say the next one with f, now x has e and f. And I can go on and keep adding elements to a list by using plus equal. But there's also another operation, well, it's a method on the object, and it's called append. And so now I can append, for instance, g. And so now x is e, f, and g. So I can use either of these ways of adding an element to the end of a list. And what's just funny to me is that plus equals works with both strings and with lists. So with that, I can go here and I can run PyTest to assure myself that this version works. And then I can go here and run this version. And without very much effort on my part, I assure myself that this version also works. So we're learning several different ways of accomplishing the same goal. Let's keep going. Using a list comprehension. So this is one of my favorite parts of Python is a list comprehension. So if we look at this this diagram here, a list comprehension essentially reverses the idea, the statements in a for loop. It puts the body of the for loop first, and then at the end says for base in args DNA. So here we have the for base part comes at the end, and the transget comes inside the code block. Basically, the code block comes first, and then the for iteration comes second. So a list comprehension is kind of backwards the way that an if expression is backwards. I showed an if expression in one of the previous chapters. So what does that look like in our code? Well, I show it here. If instead of, I can rewrite the entire for loop using, so I have my trans table here. I can rewrite this entire for loop by putting transget the base, for base in args.dna inside of these square brackets. And now I have replaced a couple of lines of code with one line of code. And let's go back and look at this. One of the reasons why I would say I prefer this one line to this 3 lines is because in this version I'm mutating this value. So complement starts off as the empty value, and then I'm adding values to it. I prefer the method where the variable gets initialized and filled with its data all in one line. And I'm willing to put a decent amount of code into this to make this one line work. The one line can actually span over a couple of lines depending on how you need to do it. Like it doesn't necessarily have to be literally one line of code if some of these need to get longer. But point is that from a functional programming standpoint, I prefer not to initialize values and then mutate them inside of a for loop when it's possible for me to do all of that work in one line. So Does this actually still work? Only the tests will tell us. The truth machine, we are running PyTest. Yes, this still works. So we still have a ground truth that we're working from. This is this is a list comprehension. If we wanted to be particularly nasty, we could stick all of this in one line. I don't recommend this, but it does technically fall within the PEP8. These are documents that have designs, ideas, kind of RFCs in a way. And it says that at one point, at least when I was writing this, PEP8 said that lines should be 79 characters or fewer, and this is technically less than that, so it does fall within the style guidelines. I think it's actually quite difficult to read, and I would not put this in my code, but I'm just letting you know that it's possible, and if you probably want to make your own life harder, then you could use that. So in chapter 2, I introduced the string replace, and we could think about using that, but there's going to be some problems with it, and so I have a whole schematic here trying to show you why this doesn't work. So if we start off with our string that we've been starting off with, and we replace all the A's with T, if you'll recall, this returns a new string. It does not replace them in the string itself. So I have to overwrite the string entirely with the results of replacing A with T. And now if we look at this, there are no A's, and in the original string there was 1 T, and now there are 4 new T's in addition to the 1 T. And so what happens is when I go to replace the T with A, now the original A's are back, because now we've replaced those when they got replaced with T's. Now they've been back replaced with A, and so we do not have the complement. We have really just messed up our string entirely, and so I'm trying to show that the A's become T's and then they become A's again. So that is not going to work for us. There is, however, a way to make one pass over the string and use that substitution table that we had to, as we're going over, replace each character and then return a new string for us. So all that work that we did for doing the lookup is done for us with this thing called translate, string translate. But string translate wants something specific for its input. It doesn't want to go from a character, from a string. It wants to go from a Unicode ordinal. So what is Unicode? Well, in the old days, one of the first representations for text was something called ASCII, the American Standard Code for Information Interchange. And it only had 128 characters because that was what they could fit into 7 bytes. And it only handled the characters that you will see on an American style English keyboard. And in that, each value is a number, and the number relates to some character. The first, I think, 32 are all kind of white space and control characters. And so if we were to look at an ASCII table, you will see that the letter A is at the value, and we can open up a terminal here. I can say, what is the ordinal value of A? And it is 65. And the ordinal value for lowercase a is somewhere else. It's separated by 32, actually, and there's some good reasons for that. And so that is what we're seeing here, that the translation table that we wrote, after we feed it through this function called maketrans, it has turned the A into its ordinal value of 65. So you can't translate something more than one character here. It needs to be a single character, and it needs to be represented by its Unicode ordinal. And I don't want to confuse the issue here. I also started talking about ASCII. ASCII only encodes a very, very small set of characters, and Unicode builds on that. So in Unicode, all the ASCII values have the same Unicode value. But what this allows us with string translate is Unicode can handle essentially every character that has been encoded now into Unicode. So string translate can do way more than just simple translation of ASCII text here. So when we feed this this kind of a translation table into MakeTrans, it's going to do the work of looking up each one of these keys and finding its Unicode value. So with that, I can also turn a Unicode value, the ordinal value, back into a character using the char function, CHR. And I mentioned this when I was talking about for, like, if we had a base, if we had some DNA of ACGT, and I said, if you were iterating over this and you wanted to say for car in DNA, that's fine because technically you're going over each character. But I pointed out that if you were to, for instance, shorten that to for CHR in DNA, print CHR, that's cool, but now this no longer works because char, if we look at it, has been left to set to T because that was the last value that we saw. And so we've actually broken Python in a very fundamental way. We've shadowed a built-in function, and that's a bad thing to do. So don't do that. Don't use char. So all of that was a long-winded way of saying that this translate, we need to turn it into a translated table. And so if we look at solution, let's see, I think this is 4. What happens is this translate, if I just simply put string MakeTrans in front of that, then we are going to get what we need. String MakeTrans. And now we have a translation table. And we can look at that in the REPL if we want real quick. We don't have to import anything because we're using the string string class, which is built in. And if we look at trans, it has indeed been turned into, those are the Unicode ordinal values. And so we can now print this, which is getting to be pretty dense. But we're translating using our translation table. We're calling, this is a bit weird. So what we're saying is that there's something called DNA. So let's set DNA equal to, oh, we'll use that string right there. It'll be fine. So if I say DNA is equal to this string, the way to call this is to say DNA translate and then pass it the translation table. And it has done that. So it's done all the upper and lowercase substitutions for us, and it has done them correctly. And that is really cool, but the way it's just a little bit backwards that we have to call this as a method on the object called DNA. DNA as a string has a translate function. The translate function needs as its argument this translation table. And so if at the end we can say reverse on that, reversed, and that's going to give us a reversed object. So we can turn that back into a string by joining it on the empty string. And now we have reversed the translated DNA. That is pretty cool. There is a slightly shorter way of writing this MakeTrans. It says, if you read the documentation, which is why I definitely recommend that you teach yourself by reading documentation, there's another way. It says, if there are 2 arguments, they must be strings of equal length in the resulting dictionary. Each character in the first string will be mapped to the character in the same position in the second string. So this is another way of writing the MakeTrans. So real quick, let's just run pytest-xv. Let's just make sure that this version works. Yes, that looks good. And so another way of writing the translation table is this, and let's make sure that works. Yes, it does. So this is, to my eye, much easier to read. I would prefer to use this version of the program. And now we have a program that is in effect 2 lines of code. Let's not discount all the work that argparse has done for us. These few lines of code that we wrote to use argparse really got us a lot of functionality that we didn't have to write. And so in the end, this is a pretty simple program, but it gets better. But wait, there's more. If we go learn about the Biopython project, we will see that there are hundreds of thousands of Python programmers who have built this incredible resource for us to use completely for free. And the only thing we have to do is install Biopython and then read their documentation to figure out how it works. Now, Biopython should be installed because that was part of the requirements that we used to set up the project. And so I can go into my REPL real quick, P3, and I can import all of Bio. It's written with an uppercase B, but I don't need all of Bio. I just need the Seq object. And so there's a really nice web page if you want to go find, and it shows you all the things that you can do with a Seq object. You can also help on Seq and read all of this, and it has pointers to HTML tutorials that you could read that are a lot easier to read than this, but it gives you a lot of ideas of what you can do with a Seq object. There's these things called mutable Seq, and there's so much to learn about, but one of the most important parts is that inside of it there is a reverse complement. So if I were to hit the slash key to search for here, and I were to search for reverse, I find the first hit is it gets me to a reverse complement. It shows me exactly how to use it. I can say Seq with given a string, give me the reverse complement of that. So that is exactly what I'm going to do. I can write it like this, or I can write it like this. I can call the Seq class and call the reverse complement function from the class and pass it the string I want, and it will print the reverse complement. So in order to use this, I'm going to go up here and I'm going to use this from Bio, import seq.io. At this point I could probably just copy it. And I'm going to replace all of this with print, let me just grab the code. Using the Seq class, call the reverse complement function, pass it args.dna. Does that work? Drum roll, please. PyTest-xv. That also works, and that is clearly the fewest lines of code that we've had to write, and the huge advantage to this is that somebody else has done all the work to write the code and also to verify that it works. It is surprisingly easy to get very trivial things wrong. For instance, I think that the first idea of a binary search, I think it was actually several years before somebody actually, the idea of a binary search is pretty simple, but I think that the first few implementations of it were flawed. It took several years for people to actually implement binary search correctly. And so you might go around thinking that you've written the perfect reverse complement function, and you in fact have some sort of a subtle bug in there. Better to go ahead and use someone else's code. There's some stuff here about MyPy that you might encounter if you're still using MyPy, but we're not going to use that. I could use TY real quick to check my REVC, and it passes. We've already seen though that TY also misses things. You kind of have to use a bunch of tools to see if there are problems with your code, but this is a pretty simple program, and the ideas here that we're really trying to learn, if we review this, what we were really trying to learn was how to expand from that if-else decision tree, kind of a very brute force way of writing something like that, and we simplified it by using a dictionary as a lookup table. And that is a pattern that I've used many times in my programs. Something else that I really wanted to explore with you is that lists and strings are actually very similar to each other, and you can even use some of the same operators like plus equal. Not always great, but it's important to know that about Python and to lean into its strengths and to understand what the sharp edges are so that you can avoid them. A list comprehension, probably one of my favorite things in Python, something that it has really borrowed from the idea of functional programming, and it essentially reverses a for loop and puts the meat of the for loop at the beginning and then puts the for part at the end and puts it into square brackets. So really useful thing to know about. We talked about the reversed function and the fact that it's lazy, and that when forced, it will return this thing called an iterator. Well, I guess it returns an iterator, and the iterator itself will, when forced, return the elements. We will see more iterators in the future. We talked about the list function. We had previously talked about the list function to create a new empty list. Here we were using the list function to coerce the values from the reversed function to actually make a new list. We talked about the string class has a make trans function, and it needs as its argument something that comes from string translate. And in talking about that, we talked a little bit about the ASCII table and how that relates to Unicode ordinals, and that's what needs to be there as the keys to make trans. That needs a dictionary that has the keys as Unicode ordinals. So that led us to talking about the ordinal function and then its complement, the char function, that will give us the ordinal value of a character, and then given a character will tell us given a ordinal value will tell us what the character is at that point. And finally, we talked about Biopython. It's a specific to bioinformatics, and it's extremely useful for you to go read as much of the documentation, or to at least know what's there, and to search that documentation when you have a question that you're trying to answer in bioinformatics. And with that, we're done with Chapter 3.